In this lecture, we are going to start talking about distributions and how to summarize those distributions. What is a distribution? Distributions are histogram shapes. We talked about histograms last class where we had a histogram looking like this. That shape of that curve is a distribution. And we're going to start talking about how to summarize distributions. A word of note here. This is the first real lecture where there's going to be equations, math. Many of you have convinced yourself beyond all reasonable doubt that you are bad at math. Stop it. Say it with me right now. I am not bad at math. I am not bad at math. Really, you're not. You have just convinced yourself that you are. Probably because at some point you had a shitty teacher that let you fall behind. Math is not evil. Math is very, very simple. It is. It really is. I promise you. And I am going to work with you as much as I can to make sure that you do not fall behind in this class. And if you feel as though you are confused or you don't understand, I really need you to contact me and let me know that you're struggling. A quick recap from last class. We had a lot of philosophy talk. Science exists to resolve the variation of nature into patterns. The probability of any event is something that quantifies the likely outcome of that event. The probability of any event lies between 0 or 1, but it cannot be 0 or 1. In other words, it cannot be guaranteed that the sun will rise tomorrow. It's a very good chance that the sun will rise tomorrow. The chance of the sun rising tomorrow is definitely somewhere between the weather pattern being correct in New Jersey, the weather predictions being correct, and absolute certainty. But it's not 100%. It's not 1. Because the sun could blow up tomorrow for all we know. Like COVID matters anymore. The sum of all probabilities in your event space must sum to 100%. Histograms display the frequency of an event. For example, measuring 50 versus 51 insects. Visiting a pitcher plant. The probability of two events occurring together is the product, you multiply it, of the probability of each of the events, and the probability of one or a second event occurring is the sum of the probability of each of those events. In our last recorded lecture, we observed 100 insects approaching 20 different plants. So we observed a total of 2,000 insects. I summarized what we found from each one of those plants. And I determined the number of insects that entered and left the pitcher plant. In my first trial, I observed 50 insects entering and then leaving the pitcher plant. In my second trial, I observed 47 insects entering and leaving the pitcher plant. In my third trial, I observed 37 insects entering and leaving the pitcher plant, 53 insects, 65 insects. In my sixth trial, I observed once again 50 of those 100 insects entering and leaving the pitcher plant. And instead of drawing it immediately overlapping, right, like right on top of the first 50 data point, I stack it. I put it on top. I do this again, 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 and again, and again, and again, and again, and again, and again. I'm sure the closed captioning is going wild with this. And again, oh, no, I'm done. I have a distribution, a shape that these points have given me. This shape looks like a camel's hump. This shape, as we will learn, is a normal distribution. That is what we call this shape. And this shape has certain properties associated with it. The location of this data tells us where the majority of data are found. Clearly, the majority of data are found there, whereas not a lot of the data are found in these tails, they're called. These are called the tails of the distribution. The spread of data in this shape describes how variable the data are. In other words, we know that most of the data fall somewhere around that line. How spread the data are around that median line is the spread or the variation of our data. The data could look like this. That's an awful line. Let me redraw that. The data could look like this, all right, where it's a fat distribution. Nothing wrong with a fat distribution. It's just a much more variable distribution. How do we find the average, or otherwise known as arithmetic mean, of this data? You guys know how to do this. You've done this since you were in kindergarten. Okay, probably not since you were in kindergarten. Maybe since you were in like 3rd or 4th grade. You know how to do this, but I'm going to give you an equation that's going to make it look like you don't know how to do this. The way that you calculate the average or arithmetic mean of this data set is you sum all of the data points and you divide that sum by the number of data points. This thing right here is a summation symbol. You add up all of the individual data points. These individual data points are referred to as our y's. All right. This right here is y1. This right here is y2, y3, y4, y5, etc., all the way to y20. This whole thingy up here tells us that we are first going to start with I is equal to 1. This one right here. We take this one and then we increase I by 1. So we add this one to y2. We increase I by another 1, so we get y3, and we add this one. We increase I by another 1, and we add this one, 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 this one. Oh my God, the closed captioning is going crazy. And all the way up to y20. Why do we stop at y20? Because n is equal to 20. N refers to the number of data points. All right, n always refers to the number of data points. And we go from I of equal to 1 all the way up to n, and n is equal to 20. So we sum up all of these data points, and then we divide that by the number of data points. All right? You know this. What is the average of, oh, I don't know, 10 and 20? How do you figure that out? You add 10 and 20 together, and then you divide by 2. So 10 plus 20 is equal to 30, divided by 2 is equal to 15. Same thing as we've always done. That is how you determine the average or arithmetic mean of this data. The only challenge is in figuring out this notation, which you do need to know how to interpret. Now, another parcel of this notation is this funky little y bar or y bar value right here. Why do we use this notation? All right. I want you to note that this y bar notation here is the notation that we use for our sample mean. When we went out to the field, we measured 100 insects visiting 20 plants. There are way more than 20 plants in the field of pitcher plants. So we have taken a sample of the pitcher plants, and we refer to that sample mean as y bar. The Greek letter mu, M-E-W, mu. The Greek letter mu is notation for the actual mean, which y bar is trying its hardest to estimate. We will never, ever, ever know mu. We can't because we're measly humans and we don't have access to the entire world. We assume that y bar approximates the true mean. But remember that statistics never gets to truth. There is no such thing as truth in statistics. So what right do we have to make the assumption that y bar approximately equals the true population mean? Well, we don't, but we're presumptuous human beings, our little peons of ourselves. If data appear to be equally centered around some mean, meaning that the spread of data over here is equal to the spread of data over here, then it is likely that adding more sample points will not make the current estimate of the mean bounce around too much. What do I mean by that, guys? All right, so let's say that I had a bunch of data points all over the place. All right, but most of the data points are stacked right in the middle. Adding more data points to this means that I'm probably going to add another data point right here. I'm probably going to add another data point right here. But most of the data points I'm going to add are right around this mean. Most of the data points that I add are going to be around the mean. And occasionally, adding a data point to this distribution will shove this mean over a little bit. That's an awful arrow. We'll shove this mean over just a little bit. It will nudge it over a little bit, but then the next time I add another number, it's going to nudge it back. And then it's going to nudge it this way, and it's going to nudge it that way. And the more data points I add, the closer and closer I'm going to resolve around this mean. If the data are equally balanced around a center mean, we call that a normal distribution. If the data are equal, if half of the curve over here is equal to the other half of the curve over here, if the area over here and over here are the same, we call this a normal distribution. Why a normal distribution? I don't know. For the same reason that we call anything normal, I guess. Anyways, this is a normal distribution. One thing to note, and this might confuse some of you, so it is worth stopping and repeating this if you need to. Using y bar to estimate the true mean assumes that you are not interfering with nature. It assumes that all observations are independent of each other. This is really critical. What if, and like I said before, we measured a bunch of data points, and if I add another data point, it's likely to show up right here, or maybe right here. And the fact that I can say that if I add more data points, they're probably going to fall within this area right here. The fact that I can say that means that I am continually taking independent data points. What if I were not to take non-independent data points? Well, if I were to take non-independent data points, it might mean that some more of the data points might start showing up on one side because maybe some of these data points influence each other. And that's not kosher, guys. You've got to have independence among your data points. One of the key assumptions. We'll talk about that more as the semester goes on, but if you were confused by that, please stop and repeat it. As a practical example of measuring things, let's measure diversity of insects in plots of land. All right, so let's take our very, very high-tech PVC grid plot and throw it down on a parcel of grass. And in that parcel of grass, we measure some insects. We measure a square insect, and then we measure a triangle insect, and then we measure a circle insect, and again we measure a triangle insect, and again we measure a triangle insect, and a circle insect, and another circle, and then another square, and so on and so on. I don't know what these insects are, it doesn't matter. Point is that we only measure 3 insect species in this plot. Then we then we do another plot over here. And we measure again, circle, triangle, but then we come across a no, let's make it a I ran out of shapes. What's another shape? A diamond. I ran out of shapes. A diamond species. All right. But then another circle, a triangle, another square, another square, another circle. All right. The point of this is that the more area you sample, the more likely it is that you're going to find a new species. However, the bulk of all species that you will find are going to be in your first plot. This is something known as the species area relationship. The more area that's sampled, the more unique species that you are likely to find, but it does plateau, meaning that it runs out. At some point, you're not going to find any new species, but the bulk of all species that you're going to find is within your first grab sample, and it slowly increases as you start to sample more and more area. This is a very classic relationship in ecology known as the species area relationship. If we were to graph this data, where we have on the x-axis each individual species identifier, and on the y-axis we have the frequency with which we collect that species. So let's say we have species number 1, we have species number 2, species 3, 4, 5, etc. We don't list all the numbers because they would overlap. We can clearly see that some species are way more dominant than others, and most individual species are fairly rare. We have a problem here because we cannot assume a normal distribution in this case. Negative values are absolutely meaningless. The shape of this distribution is not normal. It does not have an equal spread of points around both sides. So, what are we supposed to do? Well, in this case, we cannot use our arithmetic mean of the summation of all of the points divided by the total number of points. We cannot use this arithmetic mean to estimate the true mean. Instead, we have to use something else. And we use something called the geometric mean. The geometric mean is a much more accurate estimator of the true mean for log normally distributed data. The geometric mean is calculated as the nth root of the product, the multiplier, the multiplicative of all of the data points. I had trouble saying that. The product of all of the data points. What does the nth root mean? Well, if I told you it was the square root, you would just put in 2. If there were those 2 points, you know how to do the square root. Maybe you don't know how to do the cubed root. And you probably certainly don't know how to do the nth root. Don't worry, we have computer programs to deal with that. And we will, in class, show you how to do the nth root of something. But in any case, for data that look something like this shape instead of this shape, we use the geometric mean. Geometric mean, okay? And in this case, we use our y bar. Something interesting happens here, and I want to stay on this for just a little bit. No matter what the distribution, no matter what the shape of our data. Something called the law of large numbers states that with more replicates, our estimate of the arithmetic mean, y bar, will do a better and better job of predicting the true population mean, regardless of what the actual shape of our data looks like. I'm going to stress this, but I'm going to use a slightly different term here known as the central limit theorem. The CLT for short states that the distribution of large samples will always conform to a normal distribution. This, if you know statistics, should honestly send shivers down your spine. And I'm guessing that none of you are getting goosebumps as I am. But this is actually really cool, guys. Let me open this up. I want to show it to you. I'm going to show you what's happening here. Click on begin if you're doing this on your own. Let's suppose, let me zoom in here a little bit. Let's suppose that we go out to a field of pitcher plants and we measure the number of insects visiting a pitcher plant, flying in and then leaving. And we generate our histogram as we did before. Now, we had a normally distributed histogram as is shown here in this top graph. Suppose that we actually had no idea what the shape looked like. We were blind to it. We didn't do this initial sampling. Instead, what we did is we went out to the field and we measured maybe like 5 plants at a time. All right, so let's pull out 5 plants from this. And we take the average of those 5 measurements. And then we go out the next day and we pull out another 5 plants at random and we pull out the average for this. And then we do it the next day and we pull out another 5 plants and we get another average. And we do it the next day and the next day and the next day. Let's do it for 5 more days. All right, so we click on the 5. And these are the means for each one of those days. Let's do it another 5 days and those are the means. Let's do it another 5 days and those are the means. Let's do it 10,000 days in a row. And this is what we get. The mean, the average of all of our sample days, or rather the average of all of our averages, comes out to be a normal distribution. This isn't a surprise. However, let's say that our data set actually looked something like this. Now, this is where things get a little tricky. Let's suppose that this is what the true population looks like. We don't know that this is the true population because we can never know truth. But let's suppose that this is the true population. Let's, at random, select 5 data points from this. What are we doing? We're going out in one day and we're measuring 5 plants and we're taking the average of those 5 plants. We go out the next day and we take another 5 plants and we measure the average of those 5 plants. We take another 5 plants and we measure the average of those 5 plants. We go out again on the 4th day and we take another 5 samples and we find the average of those 5 samples. We do it again on the 5th day and we take the average of those and we do it for 5 more days and we get 5 more averages. We do it another 5 days and we get 5 more averages, another 5, 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 10,000 times. What is going on? Even though the data, the true data, is skewed, if we repeatedly measure our population randomly and independently, the mean of all of our sample means will be normally distributed. This is oh, I don't know, something close to miraculous. It can be explained mathematically, but this is truly amazing. Let's create a wonky data set, something that looks like this. I don't know, it doesn't really matter. Let's do that. And let's go ahead and sample it 100,000 times. No matter what our underlying distribution is, our distribution of all of our random sample means will be normally distributed. Let's go back to the lecture. We can officially just forget about log normal distributions because this central limit theorem suggests that the distribution of a large enough sample, and what's large enough, that's up for debate, but the distribution of a large enough sample will conform to a normal distribution. Now, what if we can't take repeated samples, like I just did in that example? If we can't take repeated samples, then we do have to pay attention to this. We do have to look at the log normal distribution. However, we don't have infinite number of samples. Oops. So the best that we can do is estimate mu by whatever we can possibly do. Unless we have all of the data that could possibly be measured, mu for a group of samples that appears normally distributed is best estimated as our arithmetic mean, the sum of all data points divided by n. So if our data looks like this, it's best to estimate the median, the middle point here, sorry, the median means something different, the middle grounds here, as our y bar. If the data appear log normally distributed, our best estimate of the true population mean is the geometric mean. Why am I talking about these two shapes? Because these two shapes, among the hundreds of shapes that have been described, are the two most common shapes that show up in all environmental science. When the data does not fall into a common distribution or a common shape, we can more easily describe it using the median or the mode. The median is the value in a set of observations that has an equal number of observations above and below it. So the median, 0.248 in this case, has an equal number of observations above and below it. When the mode is simply the value that occurs most frequently in a sample. Now, one last thing before we end this lecture. We have just spent a lot of time talking about how to estimate what the middle point of our distribution shape is. How can we estimate the fatness or the spread of the data of the distribution? We can do this by calculating the average squared distance of points from the mean. What does this mean? All right, well, we have our distribution shape. And let's suppose that our mean is right here. If we calculate the difference between each one of the points not on the mean and the mean, and we add up all of these line distances here, if we add them all up, these differences here are positive, these differences here are negative, If we add all of them up, we will get a big old 0. Because it's a normal distribution, there's an equal spread around that mean. Another way of saying this, if the center point is right here, oops, sorry, the center point is right here. If we add up this distance and this distance, they cancel each other out, so it's 0. This distance and this distance cancel each other out, so it's 0. This and this cancel each other out, so it's 0. All of the points on this side cancel out all of the points on this side. So what are we to do to estimate the spread of data? What we can do is, instead of adding up this and this, we square this distance. And we square this distance. And we square this distance. And we get rid of negative numbers because this number right here is a negative value, this is a positive value, but the square of -1 is equal to 1. The square of a negative value is equal to a positive value. So we square all of the differences and we add up all of those differences. What does that look like? We take the y bar, which is right here, we take the difference of each one of the individual data points with the mean, and we square them all up, we add them all up, and then we divide that value by n, or the number of data points. And this is referred to as the variance. We call this s squared. Why s? I don't know, because variance has an s in it. No, it doesn't. I don't know why we call it s. It doesn't matter. We call the variance the spread of our data. We call that s squared. And s squared is equal to the sum of all squared differences. Just as y bar estimates the true population mean, s squared estimates the true population variation. However, the value s squared constantly underestimates the true population mean. How do we know this? Look, guys, I don't know everything, and I don't know that. I don't know how we know this. All I do know is that what we usually do to better estimate the true population variation is, instead of 1 over n here, we do 1 over n minus 1. All right? Don't ask me why this is. Just remember that it's not the average sum of square differences. It's the sum of square differences divided by n minus 1. All right? This n minus 1 here is going to come back to haunt you time and time again. So just know that this n minus 1 is also referred to as the degrees of freedom. Forget this. Don't worry about this. Just don't worry about this. It's going to confuse the shit out of you. N minus 1 is just referred to as the degrees of freedom. All right? The variance is measured in whatever units that y is measured in. So if we're measuring this in grams of fish guts, or if we're measuring this in centimeters of plant height, s squared is measured in whatever units that our measurements are. So we talk about the variation in grams or the variation in centimeters squared. It is more useful because if we're talking about a y, let's say that we're measuring fish guts and we're talking about a y mean of 5 grams of fish guts, we don't want to have to talk about we don't want to have to talk about let's say 2 grams squared of fish guts. So what we usually do is, instead of talking about s squared, we take the square root of s squared just to get us s. And this is referred to as the standard deviation. We've taken this whole thing and we've taken the square root of it to get us something known as the standard deviation. S squared is equal to the variance. S is equal to the standard deviation? The standard deviation is given in the same units as y. And that's all I've got for you.